All right, welcome back. We're going to keep talking about triple integrals, and we're going to be talking about triple integrals specifically in spherical coordinates. Now, last time we talked about triple integrals in cylindrical coordinates, and before that we talked about triple integrals in the rectangular coordinate system. Right, now we have a different way to think about these coordinates in terms of spherical coordinates. And the reason they're called spherical coordinates is because we're going to be looking at small portions of a sphere to make these evaluations. All right, so before we start, let's go ahead and let's look at some simulations on Geogebra and see what we can extract from those simulations. And after we do that extraction, we'll see if we can finalize a few more items. All right, so let's go on to Geogebra. All right, here we are back on Geogebra. So let's reorient this. There we are. All right, now on the left hand side I have a few listings here for my sliders. I have rho denoted by the Greek letter, I have phi denoted by its Greek letter, and then theta again denoted by its Greek letter. And what I'm going to start doing is I'm going to start sliding these around. Now notice theta still controls the angle that is being traversed from the positive x-axis. So theta in our respect kind of looks like it's doing the exact same thing that it was doing back in cylindrical coordinates. Okay, so theta, that's awesome. Now what about rho? What can you see rho is doing? Yeah, rho looks like it's just amplifying or minimizing this object. All right, that's pretty cool. Well, what about phi? Yeah, phi is a little bit more difficult to actually extract. Now, let me close theta all the way. Let's go all the way to 2 pi. There we are. So let's see if you can capture what phi is. There we are. Go a little bit more. There we are. Look at that. That looks like a hemisphere. And you'd be right, it is a hemisphere. Let's keep going with phi. There we are. Nice. Looks like it's carving out a whole sphere. Kind of looks like the Death Star right now. That's pretty cool. Alright. So, let's keep going. And if phi goes all the way down, guess what we have? We have a whole sphere. That's why these are called spherical coordinates. They're called spherical coordinates because if we allow all of the variables to just move along their restrictions, then we will have this whole sphere to observe. Now, has anybody been able to extract what is phi? All right. Phi is actually the angle that is being made with the positive z-axis. So the positive z-axis, if phi is small, there we are. So if phi was like 45 degrees, here we are, then it just made this spherical wedge. We keep going. Phi in this case is, it went from positive z-axis, so that was phi was equal to 0, and it traversed 90 degrees. By it traversing 90 degrees, now we got a hemisphere. Nice. And if it traverses all the way to pi, so from 0 all the way to pi, it actually closes in on itself and it gets us a sphere. That's only assuming that theta was allowed to run between 0 and 2 pi. What if theta was not allowed to run between 0 and 2 pi? What if theta was only allowed to run between 0 and, let's say, pi? Right here. Again, we still have a hemisphere. So there are different ways to generate hemispheres for this sphere, and they're gonna be brought forth by these restrictions that we then need to put on rho, on phi, and on theta. All right. So now that we got this listing, let's go back over to the whiteboard. That way we can go ahead and start defining this a little bit more. All right. Here we are. So over here I have a coordinate system, my x, y, and z, and I have some point out in R space 3, which will be some point x, y, z. Now, because I have this point x, y, z, what I want to do is I want to take the exact same approach that I did last time, and I want to create this piece here. 90 degrees. This is still height of z. This here is now r. I still have theta traversing from the positive x-axis to that given length. But then I also have one more item that I want to look at, or a few more items. What I want to look at now is, I want to look at that length. That length here is given by rho. That's going to be the radius of the sphere that we're looking at. Then I want to create some sort of phi angle. Now notice on this drawing over here, and we'll get to it in a bit, but phi is the angle that is being traversed all the way till we meet that spherical wedge. So what we want then is, I kind of want the same thing. Would you agree that I could move that vector r to here, which means that's still z over here, and that's r. So the angle being made is here. Phi is the angle that is being made with the positive z-axis and the length, or the rho, of this particular point made from the point to the origin. Alright, so let's go see, and let's see if we can start extracting this to be a little bit more general. Alright, so I'm going to ask you to recall. So recall, and this is going to be basically a recall from last time. Alright, so I'm going to say from cylindrical coordinates. What we need to recall from cylindrical coordinates is that every x coordinate was given by r cosine theta, every y coordinate was given by r sine theta, and then we also had x squared plus y squared is equal to r squared. Nice. And then we also had that z, well, z was just equal to z. Okay, so I'm going to keep this in mind. Alright, so how do we want to extract this now? Now, what I want to do is I want to start extracting this, but I want to look at my middle axes here. So in here, what I did was I'm taking a view for the positive z-axis, and then I'm considering this horizontal axis to just be the x and y plane. Right? So on GeoGebra, it's as if we were to just look at the x and y plane just as a vertical line, as a horizontal line, and then the z-axis would just pop out. Now, anytime that we look at this point, anytime that we look at that point, call it here, this is P of x, y, z, we have some rho that we look at, and then after that, then we're going to have some z value here, and this is going to be perpendicular to that x and y plane. Now that x and y plane to where this meets the x and y plane, where z meets that x and y plane, that distance will always be r. Alright, now that's pretty good, but then again, our phi is right over here. So that's our phi. Now, using all of this to, let's say, manipulate that, we can actually use this to say that this here is r and this here is z. Alright, and we're going to kind of keep that in mind. Alright, and what I'm going to do is I'm going to hide these right here, because at the end of the day, we don't really need them there. We just needed them there to interpret that this was z and r. Alright, nice. So let's go through and let's extract what we need here. Alright, I'm going to do this in blue. So this extraction is going to come in blue. Here we go. Okay, so from cylindrical coordinates, we had that x. X was equal to r times cosine theta. Alright, but r cosine theta, we'll see if we can extract that just a little bit more. So from here, from this equation, let's see if we can then start extracting a little bit more. Alright, so from this equation here, and actually I think I want to do this in purple. What I'm going to do is I'm going to start extracting. Let's say cosine of phi. cosine of phi is going to be adjacent over the hypotenuse, which is rho. Nice. And then we have that sine of phi. Sine of phi is going to be opposite over hypotenuse. Nice. All right. It's looking good so far. Now, let's see what's going to happen here. Well, this piece here, this one here, tells me that r is really just rho times sine of phi. Now, that again tells me this piece here, this r value is now rho times sine of phi, but it's being multiplied by cosine of theta. Nice. And again, that's because we're using this spherical coordinate as our replacement. Now, what about y? Well, y, we use the same r value, because again, the x and y plane will produce the same value, which means this is still r sine phi multiplied, that's this piece, multiplied by sine of theta. All right, that's pretty good. Now, let's see if we can get z from here. So z from here, well, according to this piece up here, z is equal to just rho times cosine of phi, which means z in this particular case is just rho times cosine of phi. And this kind of gives us what we need for spherical coordinates. Within spherical coordinates, we actually get these specific values for x, y, and z. So here's the spherical coordinates. X is equal to rho times sine of phi times cosine theta. Y is equal to rho times sine of phi times sine theta. And then z is equal to rho times cosine of phi. Awesome. Awesome so far. Now, let's see if we can produce a little bit more. Because we're not done yet with these spherical coordinates. We still need to try to build this bridge that we want between spherical, Cartesian, and cylindrical. So let's go with one more extraction from up here. The last extraction, notice we have a right triangle here. So would you agree that the last extraction that we need would be that z squared plus r squared is equal to rho squared? Nice, I would too. So if this is going to be the case, then the very last coordinate that we have here, this piece here, is going to be x squared plus y squared, let's see, is equal to r squared. But what's r squared? R squared is going to be rho squared minus z squared, which means we're left with x squared plus y squared plus z squared is equal to rho squared. Guess what that's the equation for? Yep. It's the equation for a sphere. Which means x, y, and z will always get us this equation of a sphere, x squared plus y squared plus z squared, and it's always going to be equal to rho squared, where rho squared is this radius that we're looking at for this sphere, which again stands to reason that we have these spherical coordinates. Nice. Now let's interpret a few more things. Let's look at rho. Rho will always need to be greater than 0 because we're talking about a radii. All right, we're talking about radius. Phi is always going to be the angle moving from the positive z-axis down to the negative z-axis. That is its restriction. it must always meet that restriction at all times. All right, so now that we have all this, that's great. We now have a way to work with cylindrical coordinates, which we learned from last time, and a way to now work with spherical coordinates, which we're doing now. All right, so for the purposes of this class, we must be able to move through all three coordinate systems in order to work with integration. So let's work on this really quick example. Convert the point √6, pi4, and √2 from cylindrical to spherical coordinates. All right, let's see what we have here. So I'm going to write down everything that I know from cylindrical and everything that I know from spherical. All right, so here goes. I'm going to convert it from cylindrical, and this is going to be over to spherical. All right, so cylindrical. In cylindrical coordinates, all of those coordinates are given by some r value, some theta, and some z. All right, that's what we know. Now, also in cylindrical coordinates, we have that x is equal to r cosine theta, y is equal to r sine theta. We also have that tangent of theta is y over x, and we also have that x squared plus y squared is equal to r squared. I can use any one of these to try to convert over to spherical coordinates. All right. Now from spherical coordinates, I know all of this up here. All right. So really quickly, I'm going to go through and I'm going to start identifying what was given to me. All right. This was r. So I know from here that that's r. This is theta. And then this is z. So r is equal to √6. Theta is equal to pi4, and z is equal to √2. Nice. Now, if you remember from cylindrical to spherical, theta doesn't change. Theta is the exact same theta that we're initially observing. So when we look at this here, theta's already given to us. We don't need another theta. That means we're done, for theta at least. Now, we need to find phi, and we need to find rho. So, here we go. Let's find phi, or let's find rho. Alright, so what I'm going to do here really quick is I'm going to consider this r squared. R squared, would you agree that it's just this piece here, so that's just 6? But then using my assumption here that r squared, well, this is also equal to x squared plus y squared. Nice. Well, from this assumption here, could we say that z squared is equal to 2? Nice. So we also know that x squared plus y squared plus z squared is equal to rho squared. And now that I have x squared plus y squared being 6, this is just 6 plus z squared, which is 2. This gives me rho squared, which means rho must be, yes, positive or negative √8, but in this case we don't need the negative because our restriction is that rho must always be positive, which means we get to √2, or in other words, square root of 8. So now that we have rho, that's great. All we need now is phi. So how do we get phi then? Well, we could use z is equal to rho times cosine of phi. We know z, that's √2. We know rho, that's 2 √2. We don't know cosine of phi, but that's completely fine because once we divide both sides by 2 √2, we're going to get 1/2. and we get cosine of phi. So when is cosine of some angle phi equal to 1/2? Well, that's going to be what, 60 degrees? So pi thirds? Yeah. So in this case, phi is equal to pi thirds. So the ordered pair, or the ordered triplet that we want now, in spherical coordinates, every point in spherical coordinates is going to be given by, now I'm going to write this up here, rho, theta, phi. This is how every point is going to be given. All right. So let's go through. So here goes the ordered triplet. This was 2 root 2. Oops, excuse me. 2 root 2, comma. I need my theta. So my theta was pi fourths, doesn't change. And I need my phi. Phi was pi thirds. There we are. That's it. So this ordered pair, in terms of rho, in terms of rho, theta, phi, will be the exact same, or will lead us to the exact same point in our space 3 as if we were to use cylindrical coordinates. All right, let's work with a different one. We want to convert the point -1, 1, negative root 2 from Cartesian to spherical coordinates. Oops. All right. So we have this point, and again, I'm going to go through and I'm going to start extracting what we have so far. So in here, since they're giving us Cartesian, we know that this is going to be x, y, and z. All right, that's x, that's y, and this is z. And we have to convert all the way to spherical coordinates. All right, so let's work through some of those values, through some of those conversions. The first conversion that I'm going to want to use is going to be that x squared plus y squared plus z squared is equal to rho squared. So that's going to be -1 squared plus 1 squared plus negative root 2 squared is equal to rho squared. So that's going to be 2, 1, 1, so it's going to be 4. So that means rho is going to be 2. Nice. All right. So let's keep working. Now that we found rho, all we need to find is phi and theta. Let's see if we can go through and we can extract phi and theta. All right. Now, one of the nice aspects about this, check this out. If we have x is rho sine phi cosine theta, and y, that is rho sine phi sine theta, watch what I'm going to do here. I'm going to make my insertions for what I know. So the x here coordinate is -1, rho is 2, sine phi I don't know, cosine theta I don't know, that's okay. Going back over here, this is going to be y, which is 1. Rho I do know, that's 2. Sine phi I don't know. Sine theta I don't know. Now remember that I can take any ratio that I want from here. So what I'm going to do is I'm going to take this piece and I'm going to divide by this piece. So I'm going to take 1 is equal to, or excuse me, let me rewrite this. I'm going to say 1 equal to 2 sine phi sine theta divided by -1 divided by 2 sine phi cosine theta. And I'm going to highlight where these came from, that way you can see them. That's the denominator. and this here is the numerator. Now, the reason I want to do this is because now this will simplify. The left side just becomes -1. The right-hand side, that cancels, and we're left with sine theta over cosine theta. But sine theta over cosine theta, that's just tangent of theta. Nice. Now, if you wanted to be a little bit more direct, then we could have used this process. Tangent of theta is equal to y over x, which we had initially from cylindrical coordinates, which is perfectly fine. All right. Now, once we have this, we can solve for theta. Theta is just tangent inverse of -1. So we then got to figure out, when is tangent inverse of -1 occur? Well, that happens at all the 45-degree increments. In other words, all the pi fourth increments. So if we have these pi fourths, tangent is negative, and tangent is negative only in quadrant 2 and in quadrant 4 for the Cartesian coordinate system. So my question to you is, where is this coordinate? -1, 1. This coordinate, -1, 1, is in quadrant 2, which means my angle for tangent of theta, because theta only exists on the x and y domain, so theta must be 3 pi fourths. Please don't forget your trig. All right, so now that we have theta, great. We have theta. So we have rho, we have theta, now we need phi. Well, the way that we can get phi is just by going to our z-coordinate. The z-coordinate is going to be rho times cosine of phi. Z is -√2. Rho, as we found out, was 2, and this is cosine of phi. Divide. So at which angle measurement does cosine of phi get us -√2/2? Now remember, phi can only traverse, phi, as we see here, can only traverse from the positive z-axis down to the negative z-axis. So if it's negative, if cosine of phi is producing a negative value, that means it's not in quadrant 1 up here, or octant 1. It's going to be below the x and y plane, which means our our phi value takes on a negative angle for pi fourths, which means phi must be must be 3 pi fourths. So this ordered triplet under spherical coordinates now becomes 2, 3 pi fourths, and 3 pi fourths. That's it. That's all there is to it. Now, again, every time that we start looking at this, always go through what you have and always go through what you know about these different coordinate systems. Once you go through those different coordinate systems, then we're going to be able to extract what does this specific point look like when we're looking at R space 3. Awesome. Now, let's go ahead and let's start defining how we're going to work with integrals in R space 3. All right, so here we go. I'm going to post up the definition and then I'll release it to you guys. So I'll be back in just a bit. All right, so here's the definition that we're working with when we're working with these triple integrals. All right, now again, I have this depiction over here that what we're looking at, or what we're trying to do when we're working with these triple integrals in spherical coordinates, is that we're trying to calculate the integration over this volume that is given by this spherical wedge. So again, it's not a cylindrical wedge, but it is a spherical wedge. All right, so when we do this, we then have to identify what is our phi traversing through. So we could possibly have two different phi values that we traverse through, and we have to then be aware of that. That's going to be these guys, C and D. Well, C could be thought of as this initial angle here, All right, that's going to be the initial angle to where the next angle ends, D. So as you're looking at this wedge, it's traversing in this direction downward to D. All right, so it's traversing downward from the positive z-axis and starts at C going down to D. And that's what this says right here, that your angle phi will be bounded between these two angle values. Now theta. Theta in this particular case is the angle that's going to be measured that's traveling through here. That's what's going to be creating this circular wedge part here. So those angles for theta, we're going to have some alpha value and then some beta value that we end up at. All right, so start at some alpha, start at some beta, and we're going to traverse through that in this direction. And lastly, we need rho. Rho is going to be bounded between two surfaces, or in this case, it's going to be bounded by this outer surface and this inner surface. Those surfaces are the ones that are going to give us, this is going to be some function that could have some theta and some phi embedded in it. And this here is going to be your other function, g sub 1, that could have some theta and some phi embedded in it. All right, so this is what we're looking at. Now, one very specific aspect that our constant of integration for spherical coordinates have a constant of integration of rho squared times sine of phi, and this is going to be d rho, d theta, d phi. All right, so this is a constant of integration that we need when we're talking about integration in spherical coordinates. Very, very similar to cylindrical, but except, again, we have to make sure that we consider that we're working with spherical coordinates. So let's look at an example here. Whoops. So here goes the example. Evaluate the triple integral over the region E for 16z dv, and this is where E is the upper half of the sphere for x squared plus y squared plus z squared is equal to 1. All right, so we have this upper half of the sphere, which is x squared plus y squared is equal to 1, and that's what we're going to be integrating over. That is the region E that is being bounded. So really quickly, let's go through and let's show what we're going to be integrating. All right, so I'm going to go ahead and try to give you a really quick sketch. So there's the top of the sphere, all right, just that hemisphere that we're looking at. And again, that's going to be centered at the origin, and it's going to have a radius of 1. All right, I'll come back to that in a bit. So far, this is what we're looking at. Now, in order for me to go through and to set up this triple integral over this region for 16z dv, I then have to figure out what are my limits of integration. What are the limits of integration when we bound by phi, rho, and theta? Now, as you can probably guess, theta is going to be one of the easiest ones to work with, because at this particular time, theta, if it starts in the positive x-axis, guess what it does? It just goes all the way around, because it's giving us a whole circle, which means theta is going to move 0 to 2 pi. So theta, we automatically know that it's moving from 0 to 2 pi. Nice. All right, well, what about phi? Well, if you remember, phi is moving from the positive z-axis. If this is a z-axis, and this in here was the x-axis, and then over here was the y-axis. So from the z-axis, we actually get phi. If we start measuring it, it's moving in this direction, and it stops here on the x and y plane, which means how much did it actually traverse? Well, that means phi actually traversed from 0 over to pi halves. Nice. All right, so theta's done, phi is done. Nice. Now I just need rho. What is rho traversing through? And that was that radii. How big is that radii getting? Well, the radii could start at 0. It would just be that point. And then it could also traverse and be some sort of radius maximum of 1. Which means here we have a radius from 0 to 1. Nice. So, now that we have this, let's go through and let's start inserting what we know. So in here, let's see, we have 16z, but z, again, making our interpretation in spherical coordinates, z is just rho times cosine of phi. And all we need now is just a constant of integration. So the constant of integration here was rho squared sine phi d rho d theta d phi. All right, so let's go through. Let's see, our rho in our terms went from 0 to 1. So then the innermost integral goes from 0 to 1. Then we have thetas. Our thetas went from 0 to 2 pi, so they go from 0 to 2 pi. And then our phi went from 0 to pi halves, so it goes from 0 to pi halves. There we are. Now again, this triple integral is going to be easier to evaluate than if we were to try to set this integral up in Cartesian, in rectangular coordinate system. All right, so let's go through and let's make some calculations here to see what we get. All right, so let's see. This is 0 to pi halves. This is going to be 0 to 2 pi, and this is from 0 to 1. And this is going to be 16. How many rows? I get 3 rows. And then I get sine phi cosine phi. There we are. And this is going to be d phi, d theta, d rho. So my first integral is going to be with respect to phi. So the first integral with respect to phi, we're going to go through and we're going to evaluate that. That's going to be divided by 4, so that's going to be 4 rho to the 4th sine phi cosine phi. There we are. Evaluated from 0 to 1. Perfect. All right. Now we're going to keep going. All right, this is d theta d phi. Looking good. Equals from 0 to pi halves. This is now going to be just, I'm evaluating rho here, so that's just going to be 1. So it's going to be the integral from 0 to 2 pi, and that's going to be 4 sine phi cosine phi, and that's going to be d theta d phi. Now theta here is easy to evaluate because there is no theta here, which means theta is a constant. So because theta is going to be a constant, when I integrate, I'm just going to multiply by theta. Multiplying by theta just means multiplying by 2 pi in this case. So that's going to be 2 pi times 4, which is going to be 8 pi. So this is 8 pi times sine phi times cosine phi d phi. And I'll leave you to evaluate this integral from here. Now that we got here, it's not too bad. So if you want, go ahead, put pause on the video, take some time and evaluate this. All right. If not, I'm going to give you the answer in just a bit. So put pause, try it on your own. The answer is 4 pi. All right, not too bad. So as we integrated, when we integrated this volume here over this specific function, then we naturally get 4 pi as our final result. Nice. All right. Don't mind that, that's just my dog going crazy in the background. Yeah, she's a weird dog, so. Alright, so the next piece of information that we're going to be working with is that we want to convert this integral from 0 to 3, then from 0 to the square root of 9 minus y squared, and then the integral for square root of x squared plus y squared, and then the square root of 18 minus x squared minus y squared for x squared plus y squared plus z squared. And that's going to be dz, dx, dy. And we want to convert this into spherical coordinates. Alright, so as it looks like it's being presented to us, it's looking like it's in Cartesian, and we're going to go to Cartesian over to spherical. So Cartesian over to spherical, that's our goal here. And so we're going to work with everything that we know. All right, so I'm going to start my extraction here. All right, so let's start with the extraction. I'm going to have that these y values are bounded by these y values. All right, outermost goes with outermost, which means my y values are bounded between 0 and 3. Nice, that's by the limits of integration. Now my middlemost is my x values, so that means my x values are bounded between limits of integration. They go from 0 over to the square root of 9 minus squared. And then lastly, I have my z values. My z values, that's these ones here, they're bounded between the square root of x squared plus y squared and the square root of 18 minus x squared minus y squared. All right, so there we are. There's what we have so far. Perfect. So with all of this, we're going to be able to extract everything that we need. We're going to be able to extract some phi. We're going to be able to extract, let's see, I'm going to need a rho, I'm going to need a theta, and I'm going to need a phi. So we're going to be able to extract rho, theta, and phi from all of this. All right. Now, initially, what I want to do is I want to look at these two right here, and this is kind of going to be my domain that is being produced. So I want to take a quick sketch once again for this domain so I can try to extract what could possibly be my rhos and what could possibly be my thetas. I'm not going to be able to extract phi from here, but that's okay. I'll come back to whatever phi is. All right, so let's go through and let's find that. I'm going to sketch this really quick. That way I can get a good interpretation of what is happening. Alright, I'm going to have some x's and some y's. Alright, now again, this equation here, this equation is going to be that x is equal to the square root of 9 minus y squared. In doing so, that's going to be x squared is equal to 9 minus y squared, which means that x squared plus y squared is equal to 9, which means I have a circle of radius 3. But according to this restriction, the green restriction, my y values only go between 0 and 3, which means I'm only going to go between 0 and 3, so it's only going to be the circle that goes between the x values of 0 and this piece. Here it is. Wow, it's a really bad circle. There we are. A little bit better, not too bad. So when I'm looking at this, this is the domain that I'm looking for. So theta y's, theta values. What are the theta values traversing through? And let's see if we can spend some time and analyze that. Theta, again measured from the positive x-axis, is actually just traversing through here. That's theta. Which means theta is being bounded by 0 over to pi halves. Nice. So 0 over to pi halves, there we are. So we got theta. Theta wasn't too bad. Now let's see if we can extract rho, or let's see if we can extract phi. Alright, so right now we got theta, that one's done. Alright, now let's see what else we can try to elaborate on. What I want to focus on now is these z values over here. Alright, so I'm going to work with those really quickly. Now, working with those z values, I'm going to extract one equation that z is going to be equal to square root of x squared plus y squared. And then I'm also going to extract that z will also be equal to square root of 18 minus x squared minus y squared. Alright, now from here I'm going to say, okay, well, if these two are the z values that we're traversing through in the coordinate system, let's check out to see if they intersect. If they intersect, it's going to give me something beneficial because it's going to give me some sort of possible coordinate or some possible z value that I can then look at. So let's look at these two. When is this equation equal to this equation? Well, square both sides, and we're left with x squared plus y squared is equal to, in this case, 18 minus x squared minus y squared. Add both of the x squared y squareds to this side, and it's going to get me two of them, and then divide. So it's going to get me x squared plus y squared. 18 divided by 2 gets us 9, which means we're left with this. Now, is this the initial value that we got here? Yes. This is the exact same. Which means this automatically gives me my domain. My domain was extracting this whole circle. Now, when it extracted the whole circle, I can now start establishing what I need to be looking at. This tells me that these two surfaces intersect and they make a circle. Awesome. So when they intersect, they make a circle, and I'm going to use that to my advantage. Alright, now since I know that intersection, that's going to be awesome because now I'm going to be able to use this equation here. Now, let's see why I want to use this equation. Now, we know that they intersect, these two surfaces, and they intersect at this circle, which naturally gives us this domain that we initially observed. Now, because of that, I then want to try to extract when is the largest row amount that I need. Alright, so this here would get me that x squared plus y squared plus z squared is equal to 18, and therein lies rho squared. Which means this is all rho squared, so what can we extract that rho is? Well, if we take the square root of that, that's just going to be 3 root 2. Which means rho is 3 root 2 at its largest. We can do the same thing here to find out when it's going to be minimal, but again, minimal would just be that rho was going to be 0. So we here get that rho is going to go from 0 over to 3 root 2 at its largest. Now we need phi. So the last one, we need phi. Alright, let's see if we can extract phi. Would you agree that z is equal to rho times cosine of phi? Yep. Alright, good. Now let's see if we can then start using this to try to extract what is going to be that phi argument or that phi value. All right, so let's keep going. So here we have that z is equal to 3 root 2 multiplied by cosine of phi, but now we have to try to find that z value. Well, that z value, we actually kind of know what it is, because using this piece here, the fact that we have their intersection, given this intersection, could we then find what z value that occurs at? Sure, we can substitute in this intersection into this z value, or into this function. X squared plus 9 squared is equal to 9. Make that substitution in here. We take the square root of 9. So the square root of 9 just gets me 3. And that was this square root of 9. Cosine phi, which means that cosine of phi is just going to be root 2 over 2, which means we're going to be looking at 45 degrees. So phi is 45 degrees. So phi is 45 degrees at its largest, but at its smallest, it's all the way at the top at the z-axis, so that means it's going to be 0. So from 0 down to pi fourths, that's my phi. All I have to do now is rewrite this integral in terms of that form. So let's go. The integral from 0 to 3, the integral from 0 to the square root of 9 minus y squared, and then the integral from the square root of x squared plus y squared up to the square root of 18 minus x squared minus y squared. And this is going to be for x squared plus y squared plus z squared for dz dx dy is going to be equal to, I'm going to leave some spaces there. Now, the integrand x squared plus y squared plus z squared, would you all agree that that's just rho squared according to our process that we've learned? All right, good. Now I need my constant of integration here, and that constant is just going to be rho squared times sine phi. That's going to be d phi, d theta, d rho, or sorry, d rho, d phi, d theta. Excuse me. D rho, d theta, d phi. Apologize for that. Now the innermost integral, rho. Rho, as we found out, went from 0 to 3 root 2. So that was my rho, 0 to 3 root 2. Theta, we found out, theta goes from 0 to pi halves. And lastly, phi. Phi went from 0 to pi fourths. Now, this particular case just set to set it up. So once we have this set up, all I'm going to go through is simplify just a little bit more. 0 to 3 root 2. And this is going to be for, let's say, rho to the fourth, sine phi. And this is going to be d rho, d theta, d phi. And that's it. This is our final answer. When it asked us to convert, that's all we needed to do was just convert into that process or into that system. So again, all of the work was right up here. I showed all the work to get us down to that point, and that's pretty much it. So that is a method of triple integrals using spherical coordinates. All right, so we have now finished those sections, and the next time we're going to be talking about a change of base. In other words, changing our integrals between different coordinate systems. All right, so stay tuned for that, and I hope you all have a great day.